Hi, everybody. This lecture concerns chapter 22 of the Halliday Resnick Walker book on the e-textbook on Wiley Plus. If you're reading the OpenStax book or want to read that, it's actually, I just looked, and it's volume 2, chapter 5, section 4 is where this material starts. But the subject of today's lecture is the electric field, which is a different way of looking at electric force, which turns out to be useful, although it may not be entirely clear why it's useful for a while. So let's go ahead and I'll share my notepad here with you. So again, we're in chapter 22 of the Wiley Plus e-textbook about the electric field. And so first of all, let me try to describe the electric field a little bit. What we imagine is that there is a field in space, and it actually is a force field. So for example, let's say we have this electric field, which I'll label E. It's a vector field. So by vector field, what I mean is it has a magnitude and a direction at any point in space, right? And so what creates this electric field? Well, electric charge does, right? We're always talking about the force between two electric charges. We think of one type of charge as a source charge, a source of the electric field. It creates the electric field. And these source charges are kind of fixed in place. And we'll talk about how they create the electric field a little bit later here. But we also think of a charge that we could put in the field, right? And we would call that a test charge. Now, the test charge can feel the force from the field and will accelerate due to that force. So the test charge is the thing that interacts with the field that's created by other charges. So how do we define the magnitude and direction of this vector electric field? Well, if I put a test charge in the field, call it Q, right? I define the direction of the force to be positive or with the field for a positive charge. Now, a negative charge would go opposite the field, right? To get the magnitude of the field, we just take the test charge times the field. So F equals QE. Pretty simple expression. Or you could think of it, this is the definition of the electric field. It is the force on the charge that I put in the field divided by the charge itself, right? The test charge. Okay, so again, this is another force, but it's really got to come from Coulomb's law, right? Coulomb's law is the fundamental force or law that describes the force between electric charges. This is really just another way of looking at it. And so now that we have the expression for the force on a test charge, well, how do we actually calculate the field from the source charges? And we're going to start with point charges. Right? By a point charge, I mean just a single charge, maybe like an electron or a proton at a single point in space. So first of all, if you go back to Coulomb's law, remember that the force between two charges is that constant K times the source charge times the test charge, right? We're looking at the force on the test charge due to the source charges divided by the distance between them squared. So if I have a point source charge, I would divide, right, my force, which is Coulomb's law, by the test charge. Now, when you divide the test charge here, it cancels out, and I just end up with an expression for the magnitude of the electric field due to that point source charge. It's KQS over R squared. Or, normally in the book, they may not make the distinction clear between source and test charges. They might just write KQ over R squared. You just have to realize that the charges that create the field, right, they're not going to move. They're causing the field to take place. The charge that actually interacts with the field is the test charge. So now we have the magnitude. You can calculate the magnitude of this electric field from the source charge using this formula. What about the direction? Well, let's say you had a positive source charge, right? The electric field is going to point away from positive source charges because, again, remember our definition. If I have a positive test charge, the force is with the field. So you can see the field's got to point away. Positive charges repel. If it is a negative source charge, the field points toward the negative charge, right? So that the positive test charge would feel an attractive force and move along the field once again. Again, the negative test charges always move opposite the field. All right, so these are what our fields kind of look like from our positive or negative source charges. Be aware, right? This is really a three-dimensional thing. I should have field lines coming out of the positive charge in all directions and going into the negative charge in all directions. Now you can have electric field created by more than one charge, right? I could put a bunch of charges, or let's say I wanted the net field from these two positive and negative point charges. So what if I wanted the net field directly between them, right? Well, the electric field from the positive charge would be pointing to the right. So with the negative, maybe you could draw a field line going straight across. Now, if I was up here at another point, my electric field would be pointing away from my positive, but toward my negative, so the net field would look something like this. And if you draw these lines, you'll get kind of curving lines around the charges, and you can do that down below, right? But the electric field lines are always going from positive to negative. It's going to depend on the distribution of our source charges. What do our source charges look like? So I could put source charges everywhere here, and we'll look at in the future several situations. We'll come back to this situation, which is called an electric dipole, here in a bit. But just to summarize our general rule for the electric field due to a point charge, it is K times plus or minus Q over R squared, R hat, right? By R hat, I mean the radial direction. So if it's a negative charge, it's inward, negative R hat. If it's a positive source charge, it's outward, positive R hat, right? So this just denotes the direction is away or toward the charge. So we can have, again, a lot of charges when we set up our distribution of electric source charge. Let's look at a couple of situations here. One situation we'll deal with in the future is called a capacitor. What a capacitor is basically just two metal plates separated by a distance d with positive charge on one plate and negative on the other. Typically, the way this is set up is you'll move electrons from one plate to the other, so these have equal charges. But in this situation, the electric field between the plates is what I would call uniform, right? It's basically a constant field. And how would I calculate this field? Well, it's quite complicated, right? I've got millions of charges in each plate. What I would have to do is add up the charge or the field from each of these millions of source charges. So from this positive charge, my field would be pointing away. From this one, it would be pointing down. You can see how they kind of the Y components kind of cancel out, and you get a field that's pointed to the right, positive to negative. At the edges of the plates, the capacitor, it's going to curve, kind of like the dipole situation did. Right? And so it's not uniform anywhere where outside the capacitor, it is uniform near the center of the plates. To calculate the strength of that electric field, well, probably going to have to do some kind of calculus because we've got millions of charges really close together. We'll deal with those situations later on. The situation I do want to do a kind of calculation is going back to the electric dipole. Right? So the electric dipole again has the positive source charge and the negative source charge. Now you got points everywhere that you could calculate the electric field. what I want to do is calculate the electric field at a point directly above the center, right? So each of these little distances from that center point is d over 2. The distance above that center point I'm calling z. I want to calculate the electric field along this line. One thing that makes it easier to do for this particular case is that along this line, my electric field going away from my positive charge, right, has the same magnitude. It's the same distance from either charge. I'm saying each charge q is equal in magnitude. So if I add up my E plus coming from the positive source charge and my E minus coming from the negative, the y components cancel, right? I've got a positive y and a negative y, and all I've got are two x components to add. So I'm going to write that as 2 times my magnitude of electric field from 1 point charge, cosine theta, and that's my total electric field. It's pointing directly to the right in the x direction only. So how do I calculate the magnitude? Well, first of all, I may want to do some geometry or trigonometry to write my r in terms of z and d. So r squared is z squared plus d over 2 squared. Just Pythagoras' theorem. What about the cosine of theta? Well, this angle theta is equal to this, so cosine is adjacent over hypotenuse. D over 2r, or d over 2 divided by r. And I can write that r is the square root of z squared plus d over 2 squared. Right? 1/2 represents the square root there. Now my electric field from a point charge, E, right here, is kq over r, right? That's what we just found for a point source charge. So my E total then is 2 kq over r, whoop, this should be an r squared, sorry, kq over r squared, is my electric field, times the cosine of theta. Let's plug in all of my trigonometric relationships here. I get a z squared plus d over 2 squared for the r squared. And then from the cosine, I get a z squared plus d over 2 squared to the 1/2. Combining those gives me a z squared plus d over 2 squared to the 3/2. These twos cancel and I get a kq times d. So there's my electric field magnitude, and I may write that it's just I hat, and again, because it's pointing in the x direction. Now, this is called an electric dipole, and people often define this quantity, charge times the distance between the charges, as the dipole moment. And the letter P is often used to designate that, so you might see that in the book. So P is equal to QD. Now, one thing we can do is, what if you're really far from the dipole? Or maybe these charges are really close together, like in a molecule, for example. So maybe you're an electron flying around near a molecule like this, maybe sodium chloride, NaCl, which has positive on one side, negative on the other. I could make an approximation for that case when Z is really big. Z is much bigger than D. What I could do is neglect the D over 2 squared, right? And if I do that, if Z is much bigger than D, then I would get KQD over Z cubed, I hat. Or KP over Z cubed, I hat. That is my electric field far from a dipole along that line bisecting the charges. In the homework problems, you'll see a situation similar to this, other situations where you have to add up these electric fields as vectors. So hopefully this is an example that will help you out with that. I'll be doing other examples here as we go along. One last thing I want to point out, I often use this K is about 9 times 10 to the 9 Newton meters squared per Coulomb squared. In the book, they often, instead of using K, they write it as 1 over 4 pi epsilon 0. Right, now epsilon 0 is just another constant, but I think it's much simpler to just write K for that. So don't be confused by the way the difference in their way they're writing Coulomb's law. Hopefully that hasn't caused much confusion. Okay, I'm going to stop there for this lecture. I'll be doing a couple more here from chapter 22, but start taking a look at the homework assignments, and we'll stop at that point.